Hello everyone, I'm Sagar. The topic of my mini project is counting quotient filter. We will start with a brief overview of approximate membership query, that is AMQ data structures. Then we will look at the problem, that is drawbacks of most of these AMQs. Then we will look at the proposed solution, that is counting quotient filter, also known as CQF. Then we'll look at its design, which involves quotienting RSQF, CQF. And then we will look at the lookup performance of RSQF and space analysis of CQF. Finally, we will look at the results, conclusion, and comments. Approximate membership query, that is AMQ data structures, maintain a probabilistic representation of a set or multiset. They save space at the cost of occasionally returning false positives. They never return false negatives. In other words, if an element is present, it will always return true. But if it is not present, even then it may sometimes return true. The most commonly known example is Bloom filter. There are many variants such as cuckoo filter, XOR filter, quotient filter, etc. Let's look at how insertions work in a Bloom filter. So a Bloom filter is nothing but a bit vector of size m with k hash functions. In this example, we have m is equal to 6, which is the size of the bit vector, and k is equal to 2, which is the number of hash functions. Each of these hash functions returns an index in the bit vector. So for example, if you're trying to insert w, x, and y, the two hash functions for w return 0 and 2, which is why we set those bits to 1. And then when we try to insert x, the hash functions return 2 and 3, so we set the bit to 1. The second index bit is already set to 1, so the only new bit that we set to 1 is the third index. And even while inserting y, a similar thing happens, and the only new bit that we set to 1 is the last bit. Now, when we do the queries, if we try to query for w, we again get the positions from the hash functions. We check whether both the bits are set to 1. In this case, they are set to 1. When we try to query u, one position is set to 1, but the other one is set to 0, which means the element is not present. Similarly, when we try to query z, the two positions are already set to 1, so we return true. But in reality, this element was never inserted, which is why it is a false positive. AMQs have many applications. They are used to avoid requests or operations that result from requesting elements that do not exist. They are widely used in databases, storage systems, networks, computational biology, etc. Let's take a look at a key value storage system. So on the right-hand side, we have the storage system, which stores key value pairs. And on the left side, we have a filter, which also stores key value pairs, but it is approximate. Now, when we check for key 1, the filter says no, which means the key is not present, and that is guaranteed to be the truth. It is also not there in the storage. Now, if we query for key 2, the filter says yes. So we proceed and make a disk access request. We check on the storage system with key 2, and yes, it is indeed present. So storage also responds with yes, and then we retrieve the key 2. Now, if we try to query for key 3, the filter says yes, but it tries to access key 3 on disk on the storage, but the storage says no. And this is why this is an unnecessary disk access and an example of false positive. Now let's take a look at counting data structures. So these are nothing but AMQs for multisets. Queries return a count, that is an integer value, instead of existence, which could be just a Boolean true or false. The false positive equivalent for counting data structures is overcounting. That is, the count will be more than the actual count. And the false negative equivalent would be undercounting. And these data structures never undercount, which means the count that is returned by counting data structures could be greater than or equal to the actual count. The most commonly known examples are counting Bloom filter and count min sketch. Now let's look at why counting is important. Counting data structures have numerous applications in different fields, such as computational biology, for example, the K-mer counting. Then also network anomaly detection, and also natural language processing, for example, the n-gram counting. Also, counting enables AMQs to support deletion. Now let's take a look at the counting Bloom filter. Similar to what we saw earlier, When we try to insert W with count 4, the hash function will return 2 positions, and we increment the value at these positions by 4. So this value becomes from 0, it becomes 4, and this also becomes from 0 to 4. Then when we try to insert X with count 3, this value, which was already 4, now is incremented by 3, and it becomes 7. And this value also becomes from 0 to 3. Finally, when we insert Y, this value increments from 3 to 4, and the last index increments from 0 to 1. Note here that the counters must be large enough to hold the count of the most frequent item. Counting Bloom filters are not space efficient for skewed datasets. Let's take a look at the skewed counts. It is an interesting observation that many real datasets, in fact, have skewed counts. Let's take a look at this graph. We have frequency of the elements on the horizontal axis and the number of items with that frequency on the y-axis. So for example, the number of items with a low frequency is very high, and the number of items with a high frequency is very low. And we also have some outliers here where the frequency is 10 raised to 7, but we only have a single digit number of these elements. And despite that, since the largest element is 10 raised to 7 here, we would have to store the counter sufficient enough to accommodate that. So it would be something like 4 bytes. And this is bad because we see there are around 10 raised to 9 elements which just have frequency of 1. So we are using 4 bytes to store just a single count 1. For counting data structures, there are 2 classes. The first one being counting filters. They offer stronger guarantees on the accuracy of counts, but use more space. On the other hand, frequency estimators offer weaker guarantees on the accuracy of counts, but they can use substantially less space. A counting filter may have an error rate delta. Queries return true counts with probability of at least 1 minus delta. An example being counting Bloom filter. And frequency estimators, on the other hand, have 2 parameters that control the error in their counts. The first one being accuracy parameter epsilon, and the second being confidence parameter delta. After m insertions, the probability that a query returns a count that is more than epsilon times m larger than the true count is at most delta. An example being count min sketch. So here's the problem. Most of these AMQs have drawbacks, such as the inability to delete items, poor scaling out of RAM, the inability to resize dynamically, the inability to count the number of occurrences of each item, especially with skewed input distributions. And so here's the proposed solution, a new general purpose AMQ counting quotient filter. It surprisingly overcomes all these drawbacks. It performs extremely well both in time and space. It is smaller than many non-counting AMQs, and hence counting is essentially free. It supports deletion, counting, dynamic resizing, merging, and highly concurrent access. It uses variable-sized counters to handle skewed data sets efficiently. It has a good locality of reference, and it also scales well out of RAM to SSD. Let's look at the design of the counting quotient filter. It uses a new quotient filter metadata scheme. It minimizes the scans by using 8-bit offset array. The metadata scheme is smaller and faster than the original quotient filter. It uses variable length counter encoding method. It is efficient and has zero overhead for counters. It also uses fast implementation of bit vector rank and select operations on words by exploiting x86 bit manipulation instructions. So here are the proposed AMQs for representing a multiset. We will first look at rank and select based quotient filter, that is RSQF, which is built on top of quotient filter. It has the counting functionality, but it counts in unary, that is, it stores k copies of an element. Then we will look at counting quotient filter, CQF, which is built on top of RSQF. It encodes counters using a sophisticated scheme. Now let's talk about quotienting. It uses a hash function h to calculate the hash, or also known as the fingerprint, h of x of an element x. The only source of false positives here is collisions, that is, hard collisions. Only when 2 distinct elements x and y have the same hash, that is, h of x equals h of y, is when a false positive can occur. If x is stored and y is not, then querying y will return a false positive. Now we store these fingerprints compactly in a hash table. So we have the p-bit fingerprint h of x, and we split it into two parts. h0 of x, also known as b of x, is the q-bit quotient, which is the most significant qubits. And h1 of x, also known as p of x, is the r-bit remainder, that is the least significant r-bits. Now let's look at how we store the fingerprints. We start with an x, we pass it through a hash function to get the p-bit fingerprint h of x, then we split it into q-bit quotient and r-bit remainder. So the quotient, that is b of x, becomes the bucket index, and the remainder, that is t of x, becomes the tag. So if you're trying to insert an element u, then its quotient b of u becomes its location in the hash table, and then the remainder tu is stored in the hash table. Now at this point, it is possible that another element v could have the same quotient as u, and then it would map to the same location in the hash table. This is called a soft collision. In that case, we use linear probing to resolve the collisions. Now, as we can see in this case, both T of U and T of V have the same home bucket, which is 4. Home bucket is nothing but the original quotient. And so the question arises, just by looking at a particular remainder, can we accurately tell which is its home bucket? And the answer is no, we do not have enough information to identify its correct home bucket. And this is where we need to store some additional metadata. So how do we resolve collisions? A collision occurs when two elements x and y have the same quotient, that is, b of x equals b of y. It is also known as a soft collision. The sequence of slots with the same quotient and hence belonging to the same home bucket is called a run. RSQF uses two metadata bits to resolve collisions and identify the home bucket. Occupieds I is equal to 1 if and if there exists an element x such that quotient h0 of x equals I. Run ends of I equals 1 if and only if the slot I contains the last remainder in a run. Now there are three invariants for a run. Let's look at them one by one. The first invariant says an occupied bit vector is maintained in which the bit for slot I is set to 1 if and only if the slot is occupied. As we can see in the figure, we have a simple rank and select based quotient filter. The colors are used to group the slots that belong to the same run. So we have a purple run, a green run, and a red run. Along with the run end bit masks at the end of the run and occupied bit that indicate the home slot for remainders in that run. So for example, for the purple run, we have the occupied bit of index 1 set to 1, which means there exists a run which has the quotient of 1. And then the remainders are h1a, h1b, and h1c. And since h1c is the last remainder, we have the run ends bit set to 1 for the purple run. Similarly, for position 3, we have the green occupied bit set to 1, which means there exists a run which has the quotient 3. And similarly, the last remainder of the green run is h1 of e, and so we have the run ends bit set to 1. For the red run of length 1, we have both the occupieds and run ends bit set to 1. The second invariant says, if the quotient h0 of x of some item x is less than the quotient of some other item y, then the remainder h1 of x is stored in an earlier slot than the remainder h1 of y. For example, if we consider the two runs purple and green here, the quotient of purple being 1 and that of green being 3, then we cannot store the remainder of green before the remainder of purple. The third invariant says, if the remainder for some item is stored in some slot I, then its quotient is less than or equal to I, and there are no unused slots between the item's home slot and the slot where its remainder is stored. For example, if we consider the remainder h1 of t at position 4, then its quotient t is less than or equal to 4. And it also means that between the position 3 and 4, there will be no gaps. In other words, it will be either occupied with the current run or the previous run. Now let's take a look at the demo of insertion in RSQF, that is rank and select based quotient filter. What we have at the bottom is the RSQF with the occupieds and run ends vectors and the remainder vector. And what we have at the top is the abstract representation of RSQF. RSQF will use the linear probing, whereas the abstract representation will use chaining to represent the exact same data. So if we insert A in the RSQF, then it is stored with occupieds and run-ends bit both set to 1 at the same position. And we also insert it in the abstract representation. Now, if we insert an element D, then in the abstract representation, it is simply added to the same slot with chaining. Whereas since RSQF uses linear probing, we store it in the next available slot. And we also unset the previous run-ends bit and set the new run-ends bit. Similarly, if we add D, then we directly store it in the third bucket in the abstract representation, whereas we store it in the third position with occupieds and run-ends bit set to 1 in the RSQF. And if we insert an element E, which belongs to the same run, we do same as before, where we unset the previous run-ends bit and set the new run-ends bit. Now at this point, if we insert an element C, which has the same quotient as A and B, then we will have to move the green run by 1, and we make position for C. So we store the H1 of C in the third index, and we update the previous run-end bit and the current run-end bit. And we also move everything on the right to the right. Note that here, green and red runs overlap with the remainder, but the occupied bit of the green run remains where it was. That is the home bucket of the green run. Similarly, if we insert a new element F, then we just update its occupieds and run-ends bit to 1. Now let us look at two interesting operations, that is the metadata operations rank and select, which allow us to do the lookups. Both of these operations take a bit vector and a number as the inputs. Let's look at the first operation, rank. Rank of occupieds, 3 is basically count of ones till position 3, which is also the count of runs till 3. So for example, the index 3 is here. So the count of ones is this one plus this one, which is 2. And so count of occupieds, 3 will return 2. The second operation is select run-ends, 2. It basically finds the position of the second one. That is also the position of the second run-end. So for example, if we are looking for the run-end of 2, then we start looking at the run-ends vector and we look at the second one. This is the first one, and so this is the second one. And the position of this second one is 5. So the function returns 5. Now let's look at how these operations are used for the lookup algorithm. If the occupieds bit for H0 of X is not set, then there is no such run. For example, if we try to find an element G which has the quotient 6, then the quotient bit at position 6 is not set, which means we can say that the element G has not been inserted. Now, if the occupieds bit for the quotient is set, then we use the rank to count the number T of slots less than or equal to the quotient that have their occupieds bit set. This basically tells us the number up to and including the home slot for X. Finally, we use the select operation to find the position of the Tth run-end bit, which tells us where the run of the remainders with quotient H0 of X ends. Then we walk backwards through the remainders in that run. For example, if we were to find an element D, then we first calculate its fingerprint H of D. Then we look at the occupieds vector at the position H0 of D, that is the quotient. In this case, it would be 3, and it is set. So the next thing is we use the rank operation on the index 3, which would return 2. And then we use the select operation with 2, and that would find the second one, which happens to be this. And then it tells us that the element D belongs to the green run and it ends at this position. So we start walking backwards from this position to find element D. And so we find it at this position. Now, as you noticed, both these rank and select operations, which are used to find the position of the run-end, require linear scans on the vectors. In order to compute the position of a run-end without scanning the entire occupieds and run-ends bit vectors, we maintain an additional offsets array where O of I holds the distance from the slot I to the run-end corresponding to slot I. To save space, the offset is stored only for every 64th slot, with offsets for entries in between computed at runtime. Maintaining the array of offsets is inexpensive, and computing an offset from the nearest stored offset is efficient. To make the RSQF cache efficient, instead of storing the offset, occupieds, run-ends, and remainders arrays separately, we break them into blocks of 64 entries, which we store together. We use blocks of 64 entries, so these rank and select operations can be transformed into efficient machine word operations. Offsets are stored as 8-bit unsigned integers, yielding the total metadata overhead of 8 plus 64 plus 64 divided by 64, which is 2.125 bits per slot. Now let's see how we could perform the rank and select operations on these 64-bit words. So we use the PDEP and TZCNT instructions added to the x86 instruction set with the Haswell line of Intel processors. We calculate the select and rank operations using these instructions, and then the offset can be calculated using the 64-bit words, occupieds, and runnets with this formula. Now let us look at the lookup performance of RSQF. Lookups in any quotient filter involve two steps: finding the start of the target run and scanning through the run to look for the queried value. In both the original QF and the RSQF, runs have size O of 1 on average and O of log m over log n with high probability. RSQF does nothing to accelerate the process of scanning through the run. However, RSQF does accelerate the process of finding the start of a run by processing the metadata 64 bits at a time using our efficient rank and select operations. At high load factors, this can yield tremendous speedups since it converts 64-bit operations into single-word operations. Now let us look at how we could encode counters into this RSQF to build a CQF. The CQF saves space by repurposing some of the slots to store counters instead of remainders. If a particular element occurs more than once, then the slots immediately following that element's remainder hold an encoding of the number of times that element occurs. In this encoding scheme, the CQF stores the remainders in increasing order. A deviation from the strictly increasing pattern acts as an escape sequence, indicating that the CQF is using the next few slots to store an encoded counter rather than remainders. The counter for remainder x is encoded so that no slot holding a part of the counter will hold the value x. Thus, an end of the counter is marked by another copy of x. This is the table for the encoding scheme. So for count 1, we simply store the remainder as is. For count 2, we store the remainder twice. For this counter, since we already know that it is greater than 2, we simply store c minus 2 instead of c. And we also make sure that none of the parts of this counter is x, because x is the escape sequence. However, remainder 0 is a special case, and that is handled differently. For count equals 3, we store 3 copies of 0. And for count greater than 3, we store 0 followed by the encoded count followed by 2 zeros. And again, since we know this count is greater than 3, we store c minus 3 instead of c. For example, 5 copies of 0 are stored as 0, 2, 0, 0, where the first 0 is the remainder, the last 2 zeros are the escape sequence, and the value in between the two is the c minus 3, which is 5 minus 3, 2. 7 copies of 3 are stored as 3, 0, 6, 3, where the encoded counter 7 minus 2 is stored as 0, 6. Finally, the 9 copies of 8 are stored as 8, 7, 8. Now let's look at the space analysis of CQF. The exact size of the CQF after m inserts depends on the distribution of the inserted items. This is because of the variable length encoding of the counters. When the data structure has r-bit slots, the encoding of an item that occurs c times consumes at most 3 slots plus c log c base 2 over r minus 1 slots for its counter, which happens to be less than or equal to log c base 2 over r minus 1 plus 1. Thus, the total number of bits used to encode a remainder and its count is at most 4r plus r over r minus 1 log c base 2, which is less than or equal to 4r plus 2 log c base 2, since r is greater than or equal to 2. After inserting k distinct elements, which is less than the total elements n, there are at least k occupied slots. So r is at most p minus log k base 2. Since p is equals log n over delta base 2, this means that r is less than or equal to log n over delta base 2 minus log k base 2, which can be simplified as log n over k delta base 2. The total size of all counters is maximized when all the distinct items occur an equal number of times. That is, when c equals m over k for each item. Putting this all together, let Q be a CQF with capacity n and false positive rate delta. Suppose we initially build Q with s is equal to 1 slot and resize to double s whenever the number of used slots exceeds 95%. Then, after performing n inserts consisting of k distinct elements, the size of CQF will be O of k log nm over delta k square bits. In this graph, we see the space comparison of CQF, SBF, and CBF as a function of the number of distinct items. On the horizontal axis, we have the number of distinct items in the multiset, that is k, and on the vertical axis, we have the size of the data structure in bits. As we can see, the worst case space usage for the CQF is better than the best case space usage of the other data structures for almost all values of k. Now let us look at the performance in RAM. In all the three graphs, on the horizontal axis, we have the load factor, and on the vertical axis, we have million operations per second. As we can see, the CQF insert performance in RAM is similar to the state-of-the-art non-counting AMQs. Now let us look at the performance on SSD. Again, on the horizontal axis, we have the load factor, and on the vertical axis, we have 1000 operations per second. As we can see, the CQF significantly outperforms the cuckoo filter on all operations because of their better cache locality. And we can also notice that the throughput for cuckoo filter for lookups is approximately half of that of CQF and RSQF. This is because cuckoo filter requires 2 lookups, whereas RSQF and CQF only require 1 lookup on disk. Now let us look at the performance for skewed datasets. As we can see in all three graphs, the CQF outperforms the CBF by a factor of 6 to 10 on both inserts and lookups. In this graph, we see the slots usage versus distinct items. On the horizontal axis, we have the distinct items in millions, and on the vertical axis, we have the percentage of slots in use. As we can see, even when the counting quotient filter is nearly full, that is, most of its slots are in use, it still offers good performance on skewed data. Now let us look at the performance of CQF for some applications and also for concurrency. Here, the two applications are counting k-mers in computational biology and the FireOS benchmark, which simulates a network event monitoring task. As we can see in the left graph, the CQF performs well with real-world datasets. On the right side, we have the graph for concurrency. On the horizontal axis, we have the number of threads, and on the vertical axis, we have million insertions per second. As we can see, the average insert throughput is linearly increasing with increasing number of threads for all datasets. To conclude, this paper shows that it is possible to build a counting data structure that offers good performance and saves space regardless of the input distribution. The counting quotient filter uses less space than other counting filters and in many cases uses less space than non-counting membership-only data structures. Now, here are some of my thoughts and comments on this paper. First of all, I think it smartly builds on top of an already good AMQ, that is the quotient filter. It leverages its strengths and overcomes its weaknesses. In my opinion, the main optimizations that contribute to its good performance are the first one being x86-bit manipulation instructions for rank and select queries. The second one being maintaining 8-bit offset and blocks of Site64 to minimize the scans. Finally, it uses variable length counter to handle skewed counts. I also think that the rank and select operations have the potential to optimize other data structures. As we saw, this data structure is not just theoretical, but it is also proven to be practically useful in many applications. It has also inspired some other data structures like counting with prediction, rank and select queries with adjusted anchoring. It has also gained a lot of traction, especially in computational biology for efficient k-mer counting, as mentioned in 2 papers. The first one being Squeaker, which was written by the same author, and the second one about MQF and buffered MQF. Thank you.